So this is a section 1.2 in the book, and this covers the p-n junction. Now the interesting thing about p-n junctions happens when they are placed adjacent to each other on a single piece of silicon crystal. And here I'm showing a silicon crystal, and on the left side is the p-type, and on the right side is the n-type. And the p-type has been doped with boron, and the n-type has been doped with phosphorus. And so the p-type has the excess holes, and the n-type has the excess of electrons. And in the middle is what we call the metallurgical junction. And so this picture I've shown is at basically time equals 0. If you instantaneously doped each side of a single piece of silicon crystal. And this is not like two separate pieces of silicon crystal that you kind of glue together, that's just one piece, and then you dope each region. And so the left side is the acceptor concentration, and the right side is the donor concentration, because boron accepts electron to become negative, and the phosphorus donates an electron to become positive. And so the next section is 1.2.1, sort of the equilibrium p-n junction. And so this is after you form this silicon crystal with a doped area P and N. What does it look like? And there's no applied voltages at this point. And so we have our metallurgical junction, and then we have the n-type, which has an excess of electrons. It's high in electrons, and the p-type's high in holes. And so we have this concentration gradient. One side's high in electrons, one side's high in holes. And so we have diffusion across the metallurgical junction of electrons wanting to go over to the p-type, and the holes wanting to go over to the n-type. And so after a while, what happens is that you develop what's called this depletion region, where you have all the phosphorus ions, and there's no holes around them. And oops, I got this backwards. Sorry. You have the boron ions, and then with their missing holes, and we have all the phosphorus ions, and they're missing electrons. There's no free carriers around them at that point. And then we've developed, like I said, this depletion region, or space charge region, where there is a depletion of the carriers. And at this point, it basically develops some finite width of the space charge carrier. But you still, on each side, you have your bulk p-type semiconductor and bulk n-type semiconductor. And then in between the two is the space charge region. And so this is the picture of the equilibrium p-n junction. Now, equilibrium doesn't necessarily mean static. There's still stuff going on. It just means that's where it's sort of set up to where it's going to stop growing, that space charge region. And so just redrawing at basically the moment you make the two doping, if you could simultaneously dope them instantaneously, dope both sides with P and N type dopants. So one side's high in holes and one side's high in electrons. And this would be like at t less than 0, we'll call it, or t equals 0, whatever you want to call it. Nothing's happened now. If you could freeze at that moment in time that you made it. And now we're going to draw out, well, at this point, you have your holes on the left side and your electrons on the right side. Those are the majority carriers. And they want to diffuse to each side, like I said before. And you'll get this depletion layer where you have the boron atoms, and there's no free holes around in that area. And you have the phosphorus ions, and there's no free electrons in that area. And then you have the bulk semiconductor behind that, the p-type with excess holes, and the n-type with the excess electrons. And as I said before in the previous slide, this is the equilibrium values. And so now I'm kind of drawing out what the concentration of the holes or electrons would be as a function of distance away from the metallurgical junction. And so out here in the bulk, it's pretty uniform, and then it drops off as you get to the metallurgical junction. And so on the left is your hole concentration, on your right is your electron concentration. And because of this concentration gradient, the electrons want to diffuse over to the p-type, and the holes want to diffuse over to the n-type, because over in the p-type the holes are high concentration and in the n-type they're low concentration, and vice versa. And but at equilibrium you set up this finite width where stuff won't get any bigger anymore or move anymore. And so I've kind of drawn out one more time, mostly just for myself to sort of make sense of what's going on. And I'll just call all this positive area just one giant area of positive, and all this negative area one giant area of negative potential, negative electrostatic energy potential. And so when the holes want to move over, they kind of bounce against that big positive area, and they say, "Oh, don't have enough energy to get over that barrier." And then when the electrons are on this side and they want to move over there, it's like, "Oh, I can't get over that." A negative barrier right there. It's because they're negative. And so that built-in electric field prevents the movement. And so equilibrium is basically your force of diffusion, because the concentration gradient is matching the force of the electric field that's generated by that depletion region. And so that kind of blocks the flow, the diffusion from happening. And you can calculate this built-in barrier, this potential, built-in potential that's created by the depletion region. And again, the book gives a formula, and there's no derivations. You have to take some physics class probably where they derive it or determine it or something. And so V built in is equal to KT over E times the natural log of the acceptor concentration times the donor concentration over the intrinsic concentration of squared. And if you remember, KT over E is equal to VT. That's the thermal voltage. And then I'm just rewriting the formula with VT in there. And that and that thermal voltage was equal to 0.026 volts. At room temperature, which is 300 Kelvin. So that's the potential that I guess the carriers have to overcome if they wanted to move across that barrier. And so we'll work an example where we determine the built-in potential for a piece of a p-n junction where where it has been doped. And in the example, they give that the acceptor concentration is equal to 10 to the 16th holes per cubic centimeter, and the donor concentration is, well, donor, not holes, but oops, I forgot that. That should be Nd is equal 10 to the 17th. So if we plug that all into the built-in formula, which I just gave you, we have 10 to the 16th times 10 to the 17th over 1.5 times 10 to the 10, which we calculated earlier. And you just shove that all into your calculator. And so this is going to give you a built-in barrier of 0.757 volts or 75.7 millivolts for that equilibrium value of the space charge region or depletion region. That's the built-in voltage there. And as the book says, you can't measure this with a multimeter because new space charge regions get set up at the tips of your probe. So we're moving on to section 1.2.2, which is when you reverse bias the p-n junction. So you're applying a potential now to the p-n junction. So we're going to draw out the piece of silicon that has a p and an n-type region adjacent to each other. And now we're going to attach an external voltage supply where it's configured in a reverse bias where the n-type is now has a positive voltage applied to it, and the p-type has a negative voltage applied to it. And we call the voltage supply VR, I guess, for reverse biased. And so if we draw this out, we have our metallurgical junction, we have our depletion region, and we have a built-in field because of the depletion region, but now we have an applied field from the external voltage supply that's in the reverse bias configuration, and they add to each other. So we have E applied going in this direction, and E for the depletion region, which you call E field, I think, in the book, is going in that region. So they add to each other, and the net effect is that the depletion region grows. It gets bigger. We have more negative on this side and more positive on that side. And so now it's even harder for the majority carriers to move across that barrier. And so holes don't want to go and electrons don't want to go. So the net effect is that there's no diffusion across the depletion layer, and no current is, and therefore no current is flowing, because there's no diffusion across the depletion layer. So in reverse bias configuration, there is no current flow. It can flow if you have it a super high voltage and you get something called breakdown, which breaks covalent bonds and then basically destroys your PN diode, or PN junction in this case. Now, because you have this space charge region that has gotten bigger, and you have this charge separation, you now have what's called a junction capacitance. A capacitance associated with this being in the reverse bias configuration, and it will affect switching characteristics of a PN junction type diode or transistor, or anything that has a PN junction. And just as a side note, the voltage across a capacitance cannot change instantaneously. And if you remember from first or sophomore electronics class, you got the current in a capacitor is equal to I is equal to C times the derivative of voltage with respect to time. So if the voltage changed instantaneously, then that you imply a gigantic current. So back to this junction capacitance is equal to Cj, that's how we name it. And then we have the built-in junction capacitance, that's the equilibrium value when there's no voltage applied, and we call that Cjo for. And that's all times what is it? 1 plus the applied reverse bias over the built-in equilibrium junction potential to the minus 1/2 power. And the units are farads for this. So that's the junction capacitance when the PN junction is in the reverse bias configuration. And there is a type of diode called a variactor diode, and I don't know anything about them at the current moment. But they use the capacitance property to make electrically tunable oscillators. And these variactor diodes are operated in reverse bias mode, and they're used to make something called a Hartley oscillator. Again, I don't have any idea what that is. And they're also used to make a tuned amplifier. And their symbol is a regular diode symbol with a little the capacitor symbol stuck right on the front of the diode. So again, this is called a variactor diode. The book just gives us a short blurb on it and says we'll get into it later. And so again, this variactor diode is using the capacitance property of being in a reverse bias conditions. And they probably should have just skipped it at that point and just kind of came back to it at a later time, but I guess want you to get used to the terminology at that point. So that's not tunnel amplifier, that's supposed to be tuned amplifier. So the next is we're going to, as always, anytime we get a formula, it seems like, work an example. Example 1.6, where they want you to calculate the junction capacitance of a p-n junction at a reverse bias of 1 volt and at a reverse bias of 5 volts. And this is for a piece of silicon. And this is a p-n junction piece of silicon at a temperature of 300 Kelvin. And I've just written down that same formula from the previous page, where your junction capacitance is equal to the built-in junction capacitance times 1 over the square root of 1 plus VR, which is your applied bias, over V built in. That's the built-in equilibrium potential. And they give you that the acceptor concentration, so that'd be like boron, is equal to 10 to the 16th acceptors per cubic centimeter, and so that's your p-type semiconductor. And your donor concentration, which is your n-type, would be 10 to the 15th donor atoms per cubic centimeter. So that'd be like 10 to the 15th phosphorus per cubic centimeter. And you're to assume, since this is at room temperature, that Ni is equal to 1.5 times 10 to the 10 cubic centimeters. And they give you that the built-in junction capacitance is 0.5 picofarads. From there, you just plug it in to the formula above. So you're at 1 volt applied reverse bias. Your junction capacitance is going to equal to the 0.5 picofarads times 1 plus 1 over 0.637 volts. All of that, oops, we need to calculate VI. That's where I got the 0.637. Remember, VI is equal to VT, which is the 0.26 volts. That's your thermal voltage. And then you have to put in your concentrations of your donor and acceptor over Ni squared. And you just plug it into your calculator, and that gives you the 0.637 volts. So we have the applied 1 volt over 0.637 volts. And you run that through your calculator, and that gives you 0.312 picofarads. And likewise, at an applied reverse bias of 5 volts, you get a junction capacitance of, 5 over 0.637 to the minus 1/2 power, and that's going to give you 0.168 picofarads. So the curious thing here is that as the voltage goes up, your capacitance goes down. So having a higher voltage has a less ability to store electric charge. So this sums up this region, or is this a section, I should say.